Okay, so we know that organometallic compound we can treat as a carbon anion. Carbon anion is negatively charged, certainly will attack the electrophilic carbon. Okay, and then to maintain the octet, if if a bond forms between this organometallic, the carbon anion and this carbon, one of those 4 bonds has to break, right? To maintain the octet. Which one will break will depend on what kind of leaving group it will generate. So if you break this one, okay, what will we be getting? You are getting a hydride as a leaving group, okay? How can we approximate it, okay? Qualitatively, assess the quality of leaving group? We learning organic 1. So the approximately the quality of leaving group is related to its basicity. So the more basic leaving group is, the worse the leaving group is going to be. So H minus, if you're looking at its basicity, you can look at the conjugate acid, which is H2 molecule. An H2 molecule, do you think it's a very strong acid or very weak acid? H2 molecule. Very strong or very weak acid? We look at what acid is strong or weak. First, looking at the bond strength. Second, look at the polarity. Okay, so this HH bond is pretty strong single bond, and the polarity, the more polar the bond is, the more acidic the compound. But this one, 0 polarity. So this one absolutely one of the weakest acids combined, because 0 polarity and strong bond. So that means this one is exceedingly basic. Exceedingly basic. So this is very poor leaving group. It will not form. Okay. Now the same thing. It won't break this bond because it the same generate hydride. Okay. Now, what if we break here? If let's say break here. If we break here, you're gonna generate what kind of leaving group? This is just a carbon anion, right? Equivalent to carbon anion. And we know carbon anion, we learned in chapter 15. They're also exceedingly strong base. It's also horrible, impossible leaving group. So this kind of carbon anion is an impossible leaving group. See, it's kind of similar as say the green arrow, the carbon anion of the let's say this is a conjugate acid is this kind of thing. Okay, it's very weak. The acid. So this also is a horrible leaving group. So if then only thing left, okay, is if you break this bond, okay. If you break this bond, you're generating alkoxide ion. So the net reactions here, the R connect to CH2, and the here become alkoxide ion. Okay, alkoxide ion, its conjugate acid is just a regular alcohol. This one. Regular alcohol, they are not highly acidic, but they are not also very weak acid. So pKa of the regular alcohol, I to ask you guys to memorize. pKa of regular alcohol is about 16, and the alkane like CH3, CH3, pKa is around 6th day. Okay, so alkoxide is not wonderful living group, but alkoxide is okay living group. It's feasible living group. So this usually in organic chemistry, if living group was that alkoxide, you have to question whether it's feasible. But the alkoxide is considered limit of you know acceptable living group, okay? Because it's not horribly basic. Okay, so that's why the first I want to explain why epoxide can serve as electrophile. Second, because of the two carbons, ring carbons are electrophilic, and also it has a larger angle strength. You want to release it, but then when the carbon attacks the ring carbon, I want you to understand why you break this bond. Because if you break this bond, you are generating a reasonable quality living group. Then the reaction can proceed at a reasonable rate. Okay? So that's what happens when you have a Grignard reagent or organolithium react with epoxide. So basically, you get an alkoxide, and the the hydrocarbon group in the organic organometallic compound will extend carbon chain by two carbons, okay, and you get the primary alcohol. Okay, so that's the reaction. Okay, so just give you a few examples. Okay, just give so you have a better sense. Please note the reaction conditions. Okay, so let's say if you have this, the this reaction usually done in two steps. First, mix these two guys in a THF or diethyl ether. The second step, you add acid. So the fourth step, before adding acid, the organometallic compound, okay, with this as a nucleophilic carbon, that's what you get in the fourth step. You extend the carbon carbon chain but by two carbons, they get alkoxide. Then react with acid. Okay. In second step, you get the product. Now, just give you one example, okay? Using this application of this method to make alcohol. So if you ask to start from this one, okay, you ask to synthesize this compound, okay? So we just learned the organometallic compound can react with epoxide, can give you alcohol product, and the epoxide can extend the the organic part of the organometallic compound by two carbons, and then at the end of the two carbons they have a OH group connect to. So do the Richard synthetic analysis, so you can think about this guy could be formed by organolithium plus. Then how can we get organolithium from this guy? Certainly, organolithium they are prepared from organic halide. Okay, and organic halide obviously can be prepared from the aromatic compound by EAS reaction we learned in chapter 13. So then if we write out all the reactions in the forward direction, so it's basically start from benzene, you can take the bromine, then using iron as a catalyst, get the iron bromide, no, not iron bromide, the bromobenzene, then treat in lithium in THF, you can get the organolithium, then you just add the epoxide in THF, then in a separate step add acid, you can get the product we wanted. I want to color code this so help you know where each fragment come from. So that's the one application of using the organometallic compound react with the epoxide. Okay? I'm not only talking about simplest epoxide. So there will be other more complicated reactions with other epoxide, but we're going to talk about it in chapter 17. Okay, so we up to this point, we complete all the reactions that prepare just simple alcohol, and then and there's another class of alcohols we call diols. As name suggests, diols means alcohol has two hydroxy. So depending on type of diols, if the two hydroxy groups are far away from each other, we can using the same method. We learn that can create the hydroxy group. Just do it twice. Like for instance, we can get dialdehyde with two carbonyl groups, then undergo catalytic hydrogenation. So the nomenclature you just can read it. I'm not going to go through details. Okay? But but if the hydroxy group, two hydroxy group in a diol is on the adjacent carbon, that kind of diols we call vicinal diols. Okay? So the vicinal diols can be prepared by an interesting method. Is basically the catalytic oxidation method from alkene, as start from alkene. So the catalyst we use here is osmium tetroxide. So osmium tetroxide is this guy. Osmium tetroxide is this guy. OS, then with 4 double bond with oxygen. Okay. So many of you may notice, okay, obviously this guy, the central atom far exceeded the octet rule, but because osmium is a very, very heavy atom, it's I forgot which period, but it's beyond the third period. So you have all the DF orbitals can be involved. So it's not a surprise octet rule could be broken. But what you can see is osmium is a metal, and it's substantially less electronegative than oxygen. But it has 4 oxygen double bond, this metal. So make this metal is actually very, very electrophilic. So the osmium tetroxide is, electrophilic reagent. So and we know that the alkenes, like here, okay, is the CC double bond has a sigma component and a pi component. The pi component generally make alkene nucleophilic because of the pi electrons and very rich above and below the carbon-carbon double bond. So the alkenes are reasonably nucleophilic, not super nucleophilic, but reasonably nucleophilic. So it can react with the osmium tetraoxide, which is electrophile. Under this reaction, you can pretty much view it. The reaction happen in very similar manner as the oxidation reaction. So for those of you who forgot, go check the chapter 8. Near the end of chapter 8, you have a peroxy acid react with carbon-carbon double bond. Okay. So but basically the two double bond carbons will simultaneously bond to the electron. But the difference between the osmium tetroxide and the peroxy acid is osmium tetroxide has multiple oxygen available to bond to the ring. So to bond to the double bonded carbons. So basically in the reaction you simultaneously develop two carbon oxygen bonds with the osmium tetroxide. This gives you 5-membered ring product. So in many such reactions, if two bonds formed simultaneously, such a reaction, this is addition reaction, always it's a syn addition. Means that these two carbon-oxygen bonds form simultaneously. So there's no time for this carbon-carbon bond rotation to happen. So these two bonds always form as a syn addition. Okay? Under the osmium tetroxide is a very expensive compound, and also it's toxic. So ideally, we want to use in a small amount. So in older days, when this reaction was first discovered, the chemists actually used the 1 molar equivalent of osmium tetroxide to react with CCW. But because of its expensive and toxic, later chemists found a way to use a very small amount. So what they did is after they get this, the electrophilic addition product, they treat this cyclic osmate ester with organic peroxide. And the mostly common use organic peroxide is just tertiary-butyl, the hydroperoxide, means this one. Okay. So this guy is because of the peroxygen, two oxygen. Basically the two oxygen, there's two atoms, single bond together. Just like many peroxides, they are good oxidation agents. So this guy can oxidize this one, okay, into vicinal diol, okay, and key part is this oxide this oxidation agent peroxide can oxidize this reduce the osmate part back into osmium tetroxide. And then osmium tetroxide can react with the next molecule of alkene. And because of these two carbon oxygen bonds, okay, they always formed as a syn addition. So the net reaction, the of alkene with osmium tetroxide, then treat with the peroxide in basic environment, and the most common use solvent to tertiary butyl alcohol will give you the thin addition vicinal diet. And this kind of thin addition will only matter if your CC double bond is a part of ring. So if it's not a part of ring, you only thing you will see, okay, I have a CC double bond. Okay, if you treat with osmium tetroxide with the peroxide base in alcohol, I will just add two hydroxy group, two original two double bonded carbon. But if it's the double bond is part of ring, then you can see the consequence of thin addition. Basically, the two hydroxy group, okay, will be on the same side of the ring. That's the crucial, the stereochemistry of this dihydroxylation reaction. So it's strictly a thin addition. So then, the typical reaction condition you use is let's say if the double bond is a part of ring, and if you have osmium tetroxide, that's the catalyst. Okay. And then you have this is oxidant, and this is a solvent, and you also need a bit of base in the reaction, so you will get how should I draw the double bond to the right side? It's just looks good, right? So the two hydroxy group will be added from same side. Obviously, you could have the other one as well. So just depend on how do you from which direction you're gonna look at it. These are equivalent. Okay, these two are equivalent because this compound is not not exactly chiral. So you just depend on which way you're gonna view it. But if you do have if you have a one substituent on the ring like this, okay, now this compound becomes chiral, okay, and then in this case, so this is a solvent, okay. This guy is solvent, okay. So you can either this one or the other one. But in reality, probably both gonna fall. So the key part is two hydroxy group should be on the same side. That's the most important because of the key step, the electrophilic addition step. The two carbon oxygen bonds develop at the same time. It has to be a thin addition. So here, basically, we conclude all the reactions by which you can prepare alcohol. Now we need to look at the reaction of alcohol. So we already learned, the cytophyl reactions of alcohol. Like the first ever reaction we learn in organic chemistry is alcohol react with hydrogen halide. And if you look at the alcohol, your attention obviously, I hope there's two things about alcohol. There's a few things about alcohol. First, your attention should be on the hydroxy group, and there are two lone pairs on the oxygen. So, whenever you look at the alcohol reactivity, the most important reactivity is oxygen being nucleophilic and the basic. And then there will be something else like the hydroxy group is acidic, okay? But the most important thing is oxygen. Yeah, it's nucleophilic, okay? And that is the most important the structure element in alcohol. And this actually is if you recall the mechanism in organic one, and that is also first step because oxygen lone pair. So the first step hydroxy group, and to be exact, oxygen atom react with the proton from the hydrogen halide, have the alcohol protonated. They undergo all kind of reactions, give you the alcohol halide. And the alcohol also can react with cyanide chloride and the phosphorus bromide, convert the OH group to halogen group. And the mechanism we discussed in organic one. And the alcohol can also react with sulfonic chloride, and basically we get the alkyl sulfonate. And the value of this reaction is this sulfonate group, okay, is a wonderful living group, wonderful living group, even better than the iodine. So because in this reaction, the alkyl part does not participate in reaction. It's only only the oxygen as nucleophile react with the sulfur. So whatever stereochemistry you have on this alkyl part will completely retain it. So you have very clean stereochemistry. This again is something you learn in organic chemistry. Very clean stereochemistry. So the stereochemistry of sulfonate is exactly the same as the original alcohol. And we also learned that the alcohol can undergo elimination reaction, and the first step again is alcohol because alcohol has that hydroxy group and oxygen has lone pair on it. First step is often hydroxy group is protonated if the reaction happens in acidic environment. Okay. A mechanism I'm not going to go into detail. That's what we learn in organic one. Okay. And then now knowing some the familiar reactivities of alcohol, we will be learning a new reaction of alcohol. But it's basically it's not difficult to understand if if you recall some familiar reactivities of alcohols in organic one. Under the now this reaction happens if you have an alcohol, if you treat with sulfuric acid. And this reaction condition is fairly specific because you cannot just randomly using any acid to treat with alcohol. You need an acid that is not nucleophilic. A typical such acid is sulfuric acid. And this reaction works best for primary alcohols for the reason I'm going to explain soon. Okay? And one of the example we have here is you have one butanol. If you treat with sulfuric acid at say 120 degree, and the reaction basically if you treat with one butanol with sulfuric acid, and you have two moles of butanol molecule, and they will combine together, become a bigger molecule, and at the same time will lose a small molecule. Here is water. And such a reaction is called condensation reaction. I don't know whether we use this term before or not, but if we haven't, I'm going to introduce now. Let's say two molecules combine together, forming a bigger molecule at the same time, lose a small molecule, often water, but it doesn't have to be water. So how does this reaction happen? If you want to understand its the mechanism, so we have to think in such a reaction system. You have, if you treat it with sulfuric acid, obviously you have alcohol itself, okay? And but in addition to the alcohol, we also have protonated alcohol. So now if you look at the alcohol, you obviously at least I hope you immediately the can when you see alcohol, immediately you can think, okay, the oxygen atom is nucleophilic and the basic, like the Lewis base. So oxygen could be protonated. Oxygen atom also nucleophilic could be attacking, electrophilic carbon. And if you look at in addition to this oxygen being nucleophilic and the basic, I hope you also know that this because of carbon oxygen bond is a polar bond. So the carbon that direct bond to the hydroxy group is positive polarized. So that make this carbon, we call it alpha carbon. Let's call it alpha carbon. Okay. This is called alpha carbon. Okay. Alpha carbon electrophilic. Okay. However, up to this point, we never seen a single example where alcohol itself, okay, serve as an electrophile. We never seen it. Okay, why? Up to this point, we never seen a single example. Let's say so. We all know this carbon is positive polarized. Okay, because oxygen obviously substantially more electronegative than carbon. Okay, but we never seen a single example a nucleophile directly react with neutral alcohol. Why? We learning organic 1. Can anyone tell me why? Say we have iodide, okay? Iodide is a very powerful nucleophile, okay? But iodide will not be able to react with this one, okay? Give you the nucleophilic substitution product. This reaction does not work. Why? This reaction won't work, okay? Can anyone tell me why? This reaction does not work. Although, yeah, this carbon, alpha carbon, is electrophilic, and the iodide is a wonderful nucleophile. But yet this reaction won't happen. Why? The alpha carbon is electrophilic, iodide is a wonderful nucleophile, but this reaction won't happen. Why? Yes, iodide will contact this one because this is positive charge. Iodide will be attracted by the positive charge carbon, but the reaction will not happen. Why? It does not. You could go by SN2. It does not have to involve alpha. Okay? It does not have to. Okay? So why this one doesn't really happen? Huh? The compound is it's not unstable. But why this reaction does not happen? The thing is here, if we go back like this, it will be SN2 reaction, right? SN2 reaction, you need a good leaving group because the nucleophile push this all away. You need a good leaving group, right? But OH minus is a bad leaving group, and much worse leaving group than iodine. Much worse leaving group because OH minus is a lot more basic than iodine. Okay, so this is a a reaction. The reaction will go other way around because iodine is a wonderful leaving group. OH is a much worse leaving group. So if this one actually can react with this because iodine is much better leaving group. Okay? So you need a leaving group, and OH minus is a better leaving group. It's not an impossible leaving group. If you have the nucleophile is a worse nucleophile than this one, the reaction actually could be happening. It could be happening. Okay? But the iodine is a much better leaving group. Many orders of magnitude better than this. Okay? So that's why you cannot push this one up. Better leaving group. Okay. Now, if you have acid in the reaction, the story is completely different. Okay. So the neutral alcohol, right here. Okay. You also have a protonated alcohol. In the protonated alcohol, the what you see is two things. Okay, one, the positive charge on the alpha carbon is increased compared to this. Okay, why? Because of the hydroxy group gets protonated. Okay, so makes this one full positive charge. So it will further increase the positive charge on alpha carbon. So this is one. Okay, the positive charge on the alpha carbon increase. So makes the alpha carbon more electrophilic than the neutral alcohol. But more importantly, now the OH group is protonate become water. And the water is actually a very good living group. It's not the top of the line living group, but it's comparable to bromide. It's very good one. Okay, it's comparable with bromide. So now what you see is this is a good living group. Okay, and you have a nucleophile in the system. So yeah, you have nucleophile. So basically, a protonated alcohol is a much better electrophile than the than neutral alcohol for two reasons. First, it has a much better leaving group. Okay, this one is a much better leaving group than this one. Second, the alpha carbon also become more electrophilic. So this one can act as nucleophile. This one can act as electrophile. So let's look at the the mechanism. Okay. So that's a reaction. I'm using primary alcohol as the example, and the later I will explain why this reaction mostly happens with primary alcohol. Okay. So overall reaction, two alcohols combine together become a compound called ether, and also form a molecule of water. Okay. So acid catalyzed referred as condensation, and the most favorable for primary alcohols. Okay. So the first step is the alcohol will be protonated. I'm using ethanol as the example. Get the protonated, the alcohol. This is a bimolecular reaction because two reactants in the step, and it involves strong acid. So usually it's equilibrium reaction, the fast step. Then in the second step, a couple of neutral alcohol molecule acting as a nucleophile react with a protonated alcohol. That's the electrophile. And the alpha carbon will be attacked because of the more positive charge on alpha carbon. Plus, after protonation, you have a very good leaving group. So this neutral alcohol with oxygen as attacking atom attack here. This is SN2 reaction. This attack is standard SN2 attack, and this is the rate limiting step. Okay. And then you'll be getting basically this one push one water molecule up, and that this become the product is a protonated ether. So this thing is ether, is protonated ether. Last step is the protonated, the ether, the lose the proton to a reasonable base in such a reaction system, because this system is acidic. So the reasonable base could be the neutral alcohol or could be from the water. Either way, here we use the neutral alcohol as the reasonable base to remove the proton, give you the ether product. So what you can see here is that because of the the rate limiting step is the neutral alcohol acting as nucleophile attack the protonated alcohol. This is SN2 reaction. Obviously works best when this guy is primary, the alcohol. Because of I hope you recall from the what you learned in chapter 6, organic 1, SN2 reaction. One of the most important factor is the degree of substitution on the electrophilic carbon. So if this is a primary carbon, is generally more preferred to SN2 reaction. If it's secondary or tertiary, you might have an elimination reaction to compete with it. Okay, so that's why such ether formation reaction works best for primary alcohol. If we have a secondary or tertiary alcohol, you may have the the elimination reaction as a major reaction. So just give you example, if you let's say if you treat this one with sulfuric acid, you more likely will getting the the elimination reaction happen, because the the first step of the reaction is still will be the protonated, protonated alcohol, but the protonated alcohol may actually undergo ionization reaction, give you the carbocation. When the carbocation before the undergo elimination reaction, give you the alkene. So that's the E1 mechanism, as you learned in organic 1. So that's why such ether formation reaction works best for the primary alcohol. And the reaction actually may happen intramolecularly. The means one of the the hydroxy group will be protonated, then act as the electrophile. Then the other hydroxy group, oxygen, can be attacking here, and this can lead to a cyclic product. So this kind of reaction could be, the especially favored if the formed ring is a relatively stable ring. When we say relatively stable ring, means you have about 5 or 6, the ring atoms. The ring atoms including the carbon and the oxygen atom. Here, just the you can look at how the 1,5 pentadiol undergo cyclization if we treat it with sulfuric acid. So basically, the first step is one of the two hydroxy groups will be protonated, here we just assume the right side hydroxy group will be protonated, and then such a protonation generate a very good leaving group, okay, and also makes this carbon more electrophilic. So the other hydroxy group, which is the alcohol hydroxy group is not extremely good nucleophile, but still, nevertheless, still is a pretty reasonable nucleophile. So the oxygen, this oxygen can attack the electrophilic carbon in a standard SN2 fashion, push the water molecule off, give you the the 6-number ring here. So they just look at we can look at another example. So it's important that this acid must be non-nucleophilic. So just think about if you treat with HI, what will be happening? Okay, if you treat with HI, first step will be protonation. Okay. Now after protonation, you have the neutral alcohol could serve as nucleophile, and the iodide could serve as nucleophile. Okay. Now the thing is, if you're using a highly nucleophilic acid like HI, okay, the conjugate base of those hydrogen halide is iodide ion. This guy, okay, is 100,000 times more nucleophilic than alcohol. Okay, so even when this concentration is not very high compared to alcohol, and this iodide still will compete with alcohol for the electrophile. So that's why if you really want to ether formation reaction, you have to using an acid that is not nucleophilic, because if you use a nucleophilic acid, the conjugate base of acid will compete with alcohol to react with the electrophile. Okay? You don't want to using nucleophilic acid. So mostly commonly used acid, if you want this condensation reaction, is sulfuric acid. Sometimes phosphoric acid also okay, and the TSOH also is fine. TSOH is a kind of organic version of sulfuric acid. So those are very weak they are not nucleophilic. Okay, so you will need a non-nucleophilic acid for this reaction. Don't use hydrogen halide, because if you use hydrogen halide, okay, you certainly will get this one as a side product, and that's not something you want to get. And just give you one more example. 1, 2, 3, 4. So let's say treat. I told you that's intramolecular reaction. Intramolecular reaction. Okay. So that immediately we'll see, oh, one of the hydroxyl can be protonated. Okay. Then the other hydroxy group can do the nucleophilic attack. And this just count the number of atoms. You have 1, 2, 3, 4 carbons, then plus oxygen, so you get form 5 member ring. Okay. Okay, so these are the ether formation reaction. And the next reaction, so all the reactions of alcohol, not all the reactions, many of the reactions of alcohol we will be learning in this chapter involve the alcohol oxygen atom acting as a nucleophilic atom. The alcohol can also react with carboxylic acid. So carboxylic acid are those compounds with the carboxyl group, so the COOH group. Okay. So if you have alcohol, it can react with the carboxylic acid, and if you know the use typically sulfuric acid as a catalyst. Again, you don't want using hydrogen halide for the similar reason for the ether formation reaction, because you don't want to the acid provide competing nucleophile to mess up the reaction. So sulfuric acid is the most common used for this purpose. Anyway, alcohol can react with carboxylic acid, and if you look at this reaction, it's color coded. Okay? So what you see is the organic group from carboxylic acid will be retained in the product along with the carbonyl carbon. So what you can see is so this guy, okay, is retained in the product, okay, and the alcohol part contributes its carbon oxygen bond. So the RO, okay, the alkoxy group from the alcohol part. And the exact mechanism we're gonna talk about it in a later chapter. But what I can tell you is the alcohol, the oxygen, okay, acting as a nucleophile, attack the electrophilic carbonyl carbon, and that is involved in the one essential step in such a reaction. Okay. So the right side compound we call it ester. So ester is basically you have a carbonyl group, okay. Then one side carbonyl carbon connect to alkoxy group. So alkoxy group is a carbon oxygen bond. This is a alkoxy group, and at another side of a carbonyl, you connect to a hydrocarbon group. This is a hydrocarbon group, and the alkoxy group connect to a carbonyl. So the carbonyl ester still is a carbonyl-based compound. Just one side is a hydrocarbon group, the other side is an alkoxy group with oxygen bound to the carbonyl group. This kind of called ester. And this reaction is a reversible reaction, means the reaction can go either way. So for such a reversible reaction or equilibrium reaction, you need to apply Lashadia's principle if you want to get relative high conversion, of one of your reactant. For instance, let's say if your carboxylic acid is expensive, okay, and you want to convert as much carboxylic acid to the ester product as possible, you actually can add a large amount of alcohol. Okay, so then you can have a relatively high conversion of the carboxylic acid to the ester. So if you have the reaction reversible, okay. The other way is probably even better, because if you know the Lashadia's principle, learning general chemistry, you can add the concentration of one reactant to increase the conversion of another reactant, but even better if it can remove one product from the reaction continuously. You also can, remove the equilibrium to the right side. So because one of the products in this reaction is water, the alcohol react with carboxylic acid, give you acid and water. So more common use practice is continuously remove water from the reaction system. And this, there's actually a apparatus specifically designed for such a purpose called Beanstalk, the distillation adapter. It can help you continuously remove water from such a reaction.